Try your best. You don't have to do that explicitly, but something like that, basically. Yeah, basically that figure is showing the constraint optimization idea. Okay. All right, time to get going. So last time we talked about streaming algorithms, where you get gigantic data, so you don't save it, you work on in a streaming model. So what we did, we talked about this Morris plus for counting our stream. And then we talked about finding out how many distinct elements you have seen in the stream. Then, hashing, then Bloom filters, that kind of stuff. So in a similar vein, there is this idea called sketching. So I'll tell you sketching in two contexts. First one is matrix multiplication. Second one is just the matrix itself. So you could sketch whatever. You could sketch a document. You could sketch a graph. The main idea is like you randomly create a subsample of your object, which still preserves the main structure. And whatever that main structure depends on your problem. Okay. So here, I'll start by sketching matrix multiplication. So we have two matrices, A and B. Suppose they are huge. We don't want to do the usual matrix multiplication. We want to come up with a probabilistic way, which gives you a decent approximation quickly. Okay. So first, this we started doing last lecture in the last maybe 10 minutes. So I first need to explain to you what is this equation. Then we can go for the algorithm. So first off, like if somebody gives you two matrices A and B, let me clean this place up a little bit. And you want to multiply them. How do you do it? Well, they show us a way in whatever linear algebra course you took, right? But that's not the way. Still, people are working on improving matrix multiplication. And there is always a competition on who has the fastest algorithm. Okay? So, but a way like that we usually see in a class is like take the first row, multiply it with the first column, right? And then multiply it with the second column, keep going like that and write it out. So now we are going to do the exact same thing in a different way, and it will give us a perspective to design algorithms, which is the following. Go for the kth column instead of the row, then the kth row. Okay, so let's say I pick the first column here. These are the elements in that first column. Right? And suppose I pick the first row in the other matrix. Now, you take the first element here, and you multiply it. So let me erase equality right here. Good. And then you multiply it one by one with the stuff on that row. Okay. And then you put that stuff in. Give me a sec. Where would you put that up? I think probably you'll put it like this. And then you go for the second one. You again go multiply it with everything in that row. You put it like that. And when you finish this process, you will have a matrix. So I have a column here which has M entries. I have a row here which has P entries. M times 1, 1 times P. I'll get an M times P matrix at the end, right? Off of only first column of A and the first row of B. I'll get an M times P matrix out of this process, okay? So this is only one summand here. Pick one column, one row, multiply them, okay? So this equation is claiming if you would do it for all the columns and rows, and if you sum up all the matrices you obtained this way, you will end up getting the exact same matrix multiplication you were talking about, okay? And how does that go? Let's say if you would be taking the usual way we worked out, first row, first column, well, this guy in that operation was getting multiplied with that one anyway. And you will go like first row, second column, this guy was talking to that guy. So at the end, you're keeping track of the same operation in a different way, okay? But then this suggests now a way try to cheat a little bit and get away with it. So what's that way? Every column and row gives me a matrix, which is of the size of the matrix I was going to produce. So if your matrix A is m times n, and if your matrix B is n times p, A times B will be m times p, right? So the thing on the right-hand side has the same shape of what your target was. And now you're summing through n of them to get the exact answer. Now, don't sum all of them like our stochastic gradient descent ID. Pick some, sum those. And if you do it cleverly, maybe it will be a good approximation to actual A times B. Okay, that's sketching matrix multiplication. And how are we going to actually do this? So, you say, okay, I don't know, like I have, so in the A matrix, I have n columns. In the B matrix, I have n rows. And I'm going to subsample some of those and sum up those and try to hope this is a good approximation to the actual equality. Okay. Now I have n, and I'll pick some of them. Let's just start by picking only one, okay? If I would just go pick a column and the corresponding row and multiply, which one would be the best among the n options, right? Let's start from there, and we'll slowly build up. Okay. Now, suppose, I put some probabilities on those options, right? And then in expectation, I should hit my target. So that means if you put probability pk to this guy, multiplied with 1 over pk, so that when you take the expectation, you end up getting what you want. Because this is what you're going to do. It's going to happen with this probability. In expectation, you'll get the sum that gives you A times B, okay? This is the standard cheating trick that we have been doing in anything stochastic. So we are designing a random object. In expectation, it is equal to our actual object. But if you're executing this, you're actually just taking one of them and then multiplying and outputting, okay? Now, I did not specify those probabilities yet. We are going to try to reason what's the optimal probability assignment for this problem, okay? But that's how it's going to look. So sample one column and the row with a certain probability, multiply those, spit it out. Okay. What's the correct probabilities to get a good approximation? That's now the question we need to deal with. Again, by code, no, not by hand. Everything is on computer here. You're designing an algorithm. The point is like you're trying to minimize the number of arithmetic operations you're executing. Just think about like every multiplication is a flop, right? Number of flops, that's what you want to minimize. Because this like huge matrices representing some data or operation on data. And I do care about their multiplication. I'm trying to come up with a faster way to get that multiplication. That's what I'm trying to do. Okay, so in expectation, if I would do this with probability this, I pick this up. And John asked a good question. This you should have a way to compute it. In expectation, this would be giving me what I wanted, A times B. Okay, fine. Now, then you in expectation, it's fine. Then you go work through how much variance is there, like how much error I'm going to see, basically, deviation from the actual time. And you work through the math, it ends up coming like this. You take that row, take its norm squared. Sorry, take that column, take its norm squared, take that row, take its norm squared, and then you multiply it with 1 over pk, and you sum it up. That comes out as the variance of this operation. Now, I want to cook up this pk so that this variance is the smallest. I want to reduce the variance as much as I can. And this becomes an exercise of the type of stuff you were doing over the weekend. You write down the optimization problem, you do the Lagrange multipliers, So what do you want? You want to assign probabilities. They should sum up to 1. They should be all between 0 and 1 as numbers. And at the end, what I want is minimize the variance. Okay? And what do you do? If you take derivative of this function, what is the gradient of P1, P2, Pn? Derivative of this with respect to this will be 1. With respect to that will be 1. So gradient of this guy will be 1, 1, 1, 1, 1. And that should be equal to gradient of whatever stuff here times a lambda. You just do one constraint Lagrange multiplier, okay? And then you solve it through. Turns out this P case should be proportional to multiplication of the norms, the optimal assignment, okay? So in an implementation, what would you do? Is your matrix A comes in the first pass, you will try to just save the norms, not the whole thing, just the norm of every column, and do the same for matrix B. This way, you know this information. Then after that, you sample according to this probability, then just take that column, that row, multiply output. So the implementation usually will have two passes. First pass to collect these numbers, so I know what is the randomness I need to create. In the second pass, do the random experiment output, okay? Now, this is only doing one column, one row, okay? That's what we optimize, but you don't have to do that. You can do like 5 columns, 5 rows too. And that will be literally standard technique we talked about last time. If you have a randomized algorithm, what do you do to reduce the variance? Run it in many times, average over. That's the standard technique. Let's say your algorithm is estimating a parameter, run it 1,000 times, take the average of 1,000 estimates. This will reduce the variance 1,000 square times, okay? So that's what you're gonna exactly do here. Pick a number you like, okay? Let's see what I called it. Apparently S. Repeat the same thing we just discussed this many times. So this is one trial. It should be an I here. So you repeat the same operation I just said, some number of times you like. This is the number of times. You sum it up, you get a matrix from all of them, you sum it up as a matrix, and then you average over. And this way, you will end up reducing the variance we were trying to optimize. It's going to be divided by S squared. Yeah, that's the way to reduce the variance. So this S is up to you to pick, depending on how much resource you would like to throw at it. Yeah. And in the end, how this is going to look like when you do this, you're going to pick S columns, essentially, in your operation from your first matrix A, S columns from your second matrix B, and then what do I know about this stuff? They are picked randomly. I know in expectation, this will give me the A, this will give me the B. And then what do? I go multiply these two sampled things, and that's what I output. And then you go through the math, and turns out this is what you prove. Doing it this way, the expected error in terms of variance is the norms of the matrices that's coming in divided by the number of times you iterated it. So the number of times, if you're able to scale your matrices before multiplication, if you're allowed to scale in your operation, scale them. So if they're norm 1, for example, this is, you just get a good bang for your buck. If the matrices are pretty large already, then you'll probably have to do a lot of iteration to be sure your error is not too large. But usually when your matrices are large, you also care about the relative error rather than absolute error. So you usually have more tolerance for error anyway. So this is up to you to pick, okay? So a quick example, let's say I am trying to multiply my matrix with its transpose, say. Okay, B is literally A transpose. And then the norm of that matrix is summation of squares of singular values. And then the norm of this AA transpose comes out as apparently singular values raised to the power 4. Then if I just copy paste the theorem, the error is bounded by the norm here squared divided by S, right? And then if you want that error to be, say, less than delta times the norm of the thing, you end up repeating your S should be singular value squared divided by delta times singular value to the 4. And this looks very like a wild expression to me. Okay, let's say, I don't know, let's try to think about this. So what kind of number is that? I got this sigma I squared, and I'm squaring it. Then I'm dividing it by sigma I to the 4th. So here, if some of the sigma i's are small, they'll get much smaller. If they were big, they'll get much bigger. So it's going to amplify since I'm taking one more power. It was square here, 14, right? So what's the difference between these two? So it's looking like this. If you would do sigma r, let's suppose I'm putting these numbers in a vector, okay? Imagine like this. First entry is this, second entry is this. How many singular values are there? As much as the rank. Let's call it R, okay? So the quantity on top, let's call this, I don't know, Peters matrix vector, sigma vector for the moment. The thing on top is L2 norm of this squared. No, L1 norm of it squared. Since on top, I'm just summing up stuff, right? And the thing in the denominator will be L2 squared. Right? Square those, which will be 4 to sum it up. Fine. And since I don't have a square root, I'm squaring. Okay, this will be just sum up the coordinates. So now you're taking a vector, comparing L1 norm versus L2 norm. What does it see? It sees the sparsity pattern of your vector, actually. So it looks at your matrix and kind of cares about the dominant singular values only. It doesn't care about the whole rank. It cares about if you have, say, 5 singular values, they dominate all the rest. You get away by essentially something like 5 here. That's the main point, okay? So if they would be all looking the same, this thing will be like rank, okay? Roughly speaking. All right, so at the end, you get, this is something like a stable rank notion. So rank is a very discrete, very unstable notion. I have a matrix, I just perturb it tiny bit, the rank jumps 1, right? So it's very jumpy. It's very hard to work with jumpy stuff, okay? So this is a more stable notion of rank. You do singular values, square it, take their ratio. It's like a rank notion called, some people even call this stable rank. Literally, how many times you need to repeat? Stable rank, 1 over delta, if delta is the error you could tolerate. Okay? Right, and you do this, you get your decent estimate. That's called sketching matrix multiplication. As I said, in implementations, you would do first pass, collect the norms of those columns and rows, then do the sampling using that columns and rows norms as we shown, and then repeat the sampling some number of times, and that's it. That's sketching matrix multiplication. As I said, this is just a sketching way of matrix multiplication, and it is just a thing to sketch. People keep developing new algorithms to sketch whatever object they care about. They want to sketch documents, they want to sketch graphs, etc., etc. So it's an active field, and there is always something new. And some people combine sketching with streaming. I think they started calling it stretching. I think it's a stretch, just call it sketch or stream. But like, anyway, so yeah. Massive data, basically. Huge matrix that you don't want to multiply precisely. Or like huge vector and huge matrix, you don't want to do vector matrix multiplication precisely. At the end, you care about the output. You don't really care about the operation. Yeah. S is, yes. So S is the number of times you repeat your randomized scheme. That defines how much error you expect to get. Tolerance is something you would know from your problem, okay? So tolerance is this delta here that you should know. And then I was trying to come up with like how many times you should repeat if that's what you want. And it comes out, looks like stable rank times one over this thing. If it is like ... 1, you have to say 1,000 times the rank, roughly speaking. So, for this thing to make sense, your matrix should be gigantic. If your matrix was already less than 1,000, don't even do this, right? So it should be like millions or whatever. It's for massive data. Okay. Now, the second thing is like sketching a matrix itself. This is, people come up with interesting ideas. Now they're, of course, trying to sketch tensors, not only matrices, as we start seeing tensors all over the place. And all this stuff is also getting into tensors these days. And the notion I'm going to introduce you now, people more or less managed to generalize it to tensors already. So it's called apparently CUR decomposition. Well, what the heck is that? It's like, okay, I got my matrix A. A tautologically is A times the identity. Now I would like to find some sort of projection, which is not too far from the identity. But algebraically, A times P is a much easier to compute matrix. That's the intuition. So what kind of thing I could design, okay? So work through this. At the end, what you get will be, again, you end up sampling some columns, some number of rows, and in the middle, there is a matrix created in the correct way to connect these two to each other. That's how it is going to come out. We are going to, again, start sampling some number of columns as you like. That's up to you to pick. Some number of rows as you like. And then in the middle, the thing comes out from your choices. And there are fast algorithms to do this. So I will show you an easier to present, but non-optimal one. Then I will tell you the best result to the best of my knowledge after that. And I was talking to a friend of mine whose research is basically on this for tensors over the weekend. I checked if the results I know are the state of the art. He confirmed. So what I'll show you is a 10 years old algorithm. No one has beaten it yet. It's the second one. The first one is an easier to explain, has the same idea, but not well optimized, okay? The second result is still apparently the state of the art. Okay, so first you go by some basic observations. If you have a matrix R, I don't know, 100 times a 10 or a million times a 10 million, if you take transpose of it and multiply with it, if you get something invertible, how could that happen? Let's try to reason about this. Let's say my matrix R was, say, M by N. Then the R transpose will be N by M. R transpose would be M times M. So this invertible means my matrix had rank M, okay? For this guy to be invertible, this M should be the rank of my matrix. So that means this M is smaller than N. And rank of your matrix is that M. That's the type of stuff we are talking about. So what does it mean? It's like, well, yeah, they would call it a short fat matrix. Yeah. So the M is smaller than N. Okay, very good. You're talking about short fat matrices. Okay. And then you take them, take their transpose, multiply it. Then you suppose you get something invertible. What do I know about that thing? Well, since it is invertible, you can use it to create a projection. You don't have to follow every single detail here. This is how people come up with these ideas. I'm showing you how they build the intuition. Okay, they were playing with linear algebra, trying to imitate it in a random way, basically. Okay, so if you have that kind of matrix R, you could create projection on its row space. Don't forget, it's like short and wide, right? So I have, say, 100 rows, 1,000,000 columns. It's like 100-dimensional space in 1,000 dimensions, right? So if I'm looking at the row space. So this projects down a given vector in that 1,000 dimensions onto that 100-dimensional vector space, okay? So this is the projection on the row space of this matrix R. And if you're on that row space already, projection does nothing to you. If you're orthogonal to the row space, projection kills it all, just spits out 0. That's what a projection is, right? It's projecting on the row space. Okay, very good. Now we are gonna try to imitate this projection to be here. Because at the end of the day, I'm dealing with the row space of this guy. And everything is getting projected on there anyway. You know, if it is not there, it's killing it already. So if I can imitate that projection in a quick way, maybe that gives me a way to imitate this matrix quickly. Okay, that's like the main intuition behind this kind of stuff. All right. So what do? They say you got an m by n matrix. You pick two integers r and s. It's up to you to pick how much you want, depending on your computational resources. You sample this many columns, you make it a matrix. You sample this many rows, you make it a matrix. And then there will be a U connecting these two to each other. And the sampling those, you could do it exactly as we discussed. Like, save the norms, sample according to whatever that norm does. All right. And then the matrix that connects them is essentially imitating this projection. So this is what I will sample. So I'll try to make this part the U. That's how it is going to go. Okay. I'm trying to imitate that row space projection. And this is the suboptimal result. I'll show you a better version soon. So at the end, this was, early results. You end up getting this way, what they call CUR decomposition. You need to think about the computational complexity of computing that U. The stuff, what is that U? That U is going to be this part. This is what you sampled. This is what the projection looks like. Should be your U or an approximation of it. Since there's an inversion here, you need to be careful. Okay. So you need to check if you can do it quickly. Turns out you can. All right. And the approximation you get, the CUR decomposition, comes up with this guarantee. The norm of your matrix, 2 divided by root of that R, then 2R plus S. As you can tell, this is not a terribly strong bound, but it is a bound. Okay. If you just use this bound, you may end up using a little large RNS than you essentially need to. The optimized bound, so let me skip through this part, is here. If you want let me go slowly to explain to you what is this. Okay. This is a result by Woodruff and both cities. This David Woodruff was a faculty in CMU when I was a postdoc before UTSA. And this was his reputation. If you have a problem, go talk to David. If he doesn't solve it in like 3 hours, that's a non-trivial problem. You can work on it. Otherwise, he'll probably solve it and write the paper in the next 2 days. Literally, the amount of papers this guy writes in 1 year could get 10 years in many universities. Yeah, there is no exaggeration. You can go check out his website. Right? So yeah, take his 1 year production, probably full professor here. Right? More than my production all the entire 10 years for sure. The guy is crazy. All right, so this is what they come up with. Him and I think a PhD student of David. And also super kind person. If you wouldn't know who he is, you wouldn't realize. Like you would just see like an unassuming person. You would ask a question, he will try his best to answer. That kind of personality. I was very happy to be around and just learn. All right. So what we want is this. Pick a K, 5, 10, 100 million. That's your K. And you would like to come up with best rank K approximation to your matrix. Okay. So what would be the best rank K in theory? That would be look at the singular values of your matrix, pick the top K ones, and put the vectors corresponding to those, multiply them. That will be your best K. But for this, you need to compute the singular values and do the operation, which is already n cubed complexity. And you don't want to do that in large matrices. So this is your best rank K approximation. This would be the error that would come out of it. And you want to be epsilon close to that. And you want to do it quick, okay? And that's what they managed. So you just sample K divided by epsilon columns, K divided by epsilon rows. And then they also have a clever randomized way to construct that U. And then you end up getting this result in like n log n time or something. I forget. And I could give you the precise reference if you want to check. David Woodruff also has a monograph on his webpage. What was it called? Sketching as a tool for linear algebra, something like that. He explains the whole field very nicely. So if you're interested, you can also check the monograph. The PDF should be available for your personal use on his webpage, I think. And that's about it for the sketching stuff. Or at least that's what I have time to tell you. Now I would like to move on to some other things. Any questions or comments so far? So what we did, we talked about sketching matrix multiplication. Then we applied very similar ideas to sketch a matrix itself. And you end up getting the CUR decomposition, some sample of columns in C, some sample of rows in R, and U is the connecting them to each other. And this naive looking idea turns out to be a good idea. Yes, go ahead. So that very good question. I kind of skipped over it. So ideally your U should be this. So this was the projection on the row space. This is the R we sampled. Or like, suppose this is the whole R, whole rows, for example, for a second. This would be what you will do ideally. Your matrix is projecting everything on its row space anyway. Okay. We want to do something similar to this in a quick way. So we sampled an R. If your R is small already, you can just compute your U. If it is a little sizable, then you need to come up with tricks to speed up this part. So you may do one more approximation. You don't literally compute this U, you compute an approximation. And they work out all those details, basically. And I was surprised, like, after 10 years, there is still nothing better. According to my friend who is an expert on this. All right, so that's about it. Any other questions? Okay, so this comes into game when you're dealing with massive data. And of course, if you're going to use this stuff in practice, there will be other considerations, which is if you have the infrastructure or if your company is happy with this kind of stuff. But they do always speed up operations when they get implemented. So I'm not in industry, so I don't know the latest status. From what I hear from my friends, in grad school and undergrad, slowly these academic ideas are making their way to implementations. If you want to learn more about this, there is a recent book, a thin and nice one called Algorithms for Massive Data, or Algorithms and Data Structures for Massive Data. There is this kind of stuff and more, depending on what you want to do. Okay. All right. So now let me go to the next discussion. Okay. So next discussion is going to be about, don't look at what's on the screen yet. It's going to be about dimensionality reduction, ultimately. Okay. However, to understand it, we need to talk about something called concentration of measures. Okay. So what the heck that means, I'll explain it to you. Right? So the main idea is things in high dimensions are a little counterintuitive at first, but after you get used to them, they become much easier to deal with than low dimensions, surprisingly. If what I just said sounds crazy, normal, when I first saw this stuff, it also looked crazy. After you deal with it, you train your intuition, you get used to it. Turns out high dimensions are actually much more easier to handle than low dimensions. It's just that they don't behave like our 3D world. That's why first they look weird, okay? So this concentration of measures is a thing that first looks weird, then after you get used to it, you start using it for a whole bunch of algorithm design. Okay, but I want to go there slowly. So let's say I take a cube, okay? -1 to the 1 to n. I have edges, n of them, -1 to 1. And now I want to take a little smaller cube, -1 plus epsilon, 1 minus epsilon. Smaller is supposed to be inside in my bad drawing. And then there's a little bit left between the small one and the big cube, right? Now the question is like, if I just sample a random point inside this big 1, 1, 1 cube, how likely is it to go hit that red part? You know, it's like this smaller one was almost there. It's just epsilon smaller than my big cube, right? So big cube is 1, and the small guy is 1 minus epsilon. So literally the distance here is epsilon. Distance here, there is also epsilon, right? So I got here epsilon. I got there epsilon as well. So intuitively, you would think, no way, you know, that's very less probable. And when you compute it, it comes out as like almost 1. So if you sample a random point, with very high probability, you end up going in that red region. Somehow the measure concentrates there. Okay, so let's do the computation. It's not magic. So the big one, so what does it mean to sample uniformly? It goes according to how volume of it, right? How big is that place? So the volume of the whole thing is, of course, okay, not 1, it's going to be 2 to the n because the edges are 2. For now, suppose edges are 1 to make it easy, okay? It's going to be 1 times 1 times 1 times 1, 1, fine. The smaller one would be 1 minus epsilon to the n. And let me remind you a very useful approximation. If you have a small x, 1 minus x over 1 over x is like e to the minus 1. Okay. So if you plug that in here, this guy ends up being like e to the minus n times epsilon. And epsilon is a fixed thing, right? So you fix the epsilon, dot, 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 1. As your n gets bigger, this is almost like e to the minus n. So the volume of that smaller cube is rather small, turned out, even though it's just epsilon less than the bigger one. The remaining volume is 1 minus this. That's where you're going to end up going probabilistically. And this type of stuff happens in anything high dimensional. So first, cube is, maybe you say cube is too pointy. Maybe it's a weird thing, okay? Then you start looking at other shapes. Now, the next thing I'll look at will be literally ball, the most rounded thing you could think about, right? So first question is like, so far, by the way, before I do anything else, is everything clear so far? So since a random point ends up concentrating in this red region, that's what we call as concentration of measure. So the main question here is like, I have a random vector with respect to some probability, some distribution. How does it look? Where does it live with high probability? That's what you're trying to understand. Because if you understand it, you can use those random vectors for your benefit. Yeah. Go ahead, Adam. Go ahead. Yeah, feel free. N-dimensional cube. I couldn't draw an n-dimensional hypercube, so I ended up drawing a 3D. I'm sorry for that. I could maybe try to draw a 3D projection of a 4D. That's as much as I could go. Yeah. So what you do is like you have 1, 1, 1, 1, 1 edges for the big cube. And then the smaller one is 1 minus epsilon. That's all. It sits inside. So the edge length looks almost like the bigger one. So you expect the volume to come out very similar. But when you compute, the volume comes out rather small. Turns out the smaller one is very unlikely to hit that if you pick a random vector. So that's what I was trying to say. Okay. Now we are going to try to do similar ideas on ball instead of cube. Let's say if my vectors have norm 1 or 100 or 10, and how do they look? But they should be high dimensional, okay? Here, n you could think about as the number of features of your database. Okay? That's what the dimension is for us. Or if you're thinking about weights of your neural net, number of weights. It's a big number. Okay. All right. Now, first question is like, it's easy to compute the volume of the cube. Just multiply the edges, right? But a priori, it's not even clear what's the volume of a unit ball, right? In high dimensions. In 2D, what I'm trying to say is like, imagine in 2D, I got my unit circle, right? From 0 to here, 1. And I'm trying to compute the area of this, pi r squared, right? So it's going to be pi. I'm glad I remembered this. All right. And then I don't remember the same formula for example, 3D. Okay. The question is now, if you draw an n-dimensional ball, what would be the volume of that thing? Okay. So that I could start reasoning similar way, like if I shrink it a little bit, etc. So here's the trick to do this kind of stuff. You always call Gaussians to the rescue when you get stuck. Okay. So first observation is this area. This thing also has a boundary, which is a circle right here, right? The whole thing is the ball, and the boundary is the circle. In 3D, the whole thing will be the ball, the boundary will be the sphere. So the sphere has a surface area, and in 2D, circle has a length. The area formula is pi r squared. The length of the circle is pi times r, 2 pi r, right? Okay, yeah, 2 pi r. Okay, and then what happens is like to go from the surface area to the volume of the unit ball, you divide by 1 over n. And the reason for this is like if you would be trying to compute, say, volume of a pyramid, what do you do? Base area times the length, then you divide it by 3. So in n dimensions, you divide by n. Okay, so that means if I can compute that surface area, I also get an idea about the volume, so I can go with that as well. They're all more or less the same thing. Fine. How do I compute that sphere's surface area? As I said, we will call Gaussians to the rescue. So two things we will use. This function, this weirdo-looking function, is a very nice and special one. It's called Euler's gamma function. And we have very good approximations to it implemented already in whatever package you're using. Okay. So, and a good approximation mathematically looks like this. That could be any number. Think about integers for the moment. Okay. And this kind of formula shows up when you try to compute volume of this kind of stuff. I forgot how Euler come to it. These are called special functions. And people keep working on implementing them better since they keep showing up all over the place. Yeah. All right. And I guess the best might be in Mathematica, but Mathematica is rather expensive. So still, any package you're using should have a decent approximation to this function. Okay. Anyway, so we'll use that function and the Gaussian. What do we know about Gaussian? This is the density, right? X1 squared, x2 squared, xn squared. And if I integrate it all over the place, since it's a probability distribution, I should get 1. But you forget in density, there was this, also this guy. So this should be divided by here to get 1. If you did not divide, it shows up back. All right, fine. Now, look at that Gaussian expression. This guy right here, right? Now, what I want to do is like, I want to see Rn written out of a whole bunch of spheres. Imagine like a sphere is a shell, unit sphere, 1.001 sphere, 1.002 sphere, Keep making, you start from a dot, literally 0 sphere, and you keep making small shells to cover your entire Rn. And you can write down the formula on the left as an integration on that spheres. And your T will be the radius of that sphere, and it should go from 0 till infinity. Okay, the thing on the left. So pictorially in 2D, what I'm trying to do is like I'm taking the whole plane, and I'm starting with a dot, and I'm drawing little circles. All of them will give you the whole plane. That's what I'm trying to do. All right. And now the point is, on a sphere, the norm will be a fixed number. I'm on the sphere. That means my norm is 3, right? That's what a sphere is. Every vector with a certain norm. And that makes this Gaussian density super easy to deal with. you end up going through it, and at the end, you end up getting a formula for your volume, okay? I'm not gonna bother you going through all this. Only one little thing I wanna say is like, you say volume of that sphere times a fixed number. That's what I'll get from here. dt will keep going, right? And what is the surface area of that sphere with radius t? It's gonna be whatever the surface area with radius 1, t to the n minus 1, because it's an n minus 1 dimensional object, okay? So in 2D, what is the length of the circle with radius 1? 2 pi r, 2 pi. What is the length of a circle with, say, radius t? 2 pi t. You multiply it with t, because you're in 2D, the object itself is 1D, right? And if you're in dimension n, the object is an n minus 1 dimensional guy. Instead of multiplying with t, you multiply with t to the n minus 1, and you end up getting that Euler gamma function. You go through it. At the end, this is what you get. Turns out the unit ball in n dimensions has volume about 2 times e times pi divided by n raised to the power n over 3. And as this n gets a little bigger, you would see this number is rather small. Okay. So it turns out in high dimensions, unit ball has a very small volume. So suppose I want to have volume 1, like the cube. How big should be my radius? You just flip this basically. Turns out you need to have about square root of n. So if you want to have a ball in n dimensions, and you want to have about volume 1, turns out the radius you need is this, roughly speaking. Okay? So now that's what I'll work on. I want to have a unit volume, so things are easier. Now, suppose I got this radius to myself, and we will end up saying, okay, this is my bad drawing for that unit ball, okay? Now what we will do is like, we will do a slice, okay? Let's say I go, this is my central slice, right? I go a little right, slice it, a little left, slice it. I'm taking like a slab of my big ball. And turns out, huge part of the volume lies exactly there. You just go, let's say, your radius is about square root of n. As n gets big, this is a huge number. Turns out you go right like 2, you go left like 2, you cut it, 95% of the volume is right there. That's how concentration of measure comes out on the ball. Very strange. Yes, correct. Yeah, here it's like on the side. Yeah, exactly. Yeah, exactly. All this stuff looks strange at first. So you get used to it eventually. And the way to compute it is not too hard. And it also comes out surprisingly nice. You say, okay, I go X much. Here's my radius R, which is like this. What is the length here? You just do Pythagorean theorem. It's like R squared minus X squared, something like that. And then you compute the volumes and stuff. And funny enough, it comes out almost like Gaussian. Okay. So being outside of that X almost literally looks like Gaussian. And then you plug in your Gaussian stuff. So if you have a Gaussian with unit variance, if you want to have 95% of your density, how much you should go left and right, you look up your Z table. It's about 2, okay? So that means if I go right 2, left 2, turns out that slab is like 95% of the volume. Okay, very good. And I'll give you a small cute exercise doing this, not the ball literally if I am on the sphere boundary, how does it look, etc. Now, what we will do in most applications is the easiest or nicest thing to use is Gaussians. Now I will tell you about how does concentration of measure look when I endow my space with Gaussian measure, okay? Suppose I have a random vector with n coordinates. I am in Rn. This is my random vector. And here every xi is Gaussian with unit variance. They are independent from each other. That's my random vector. if you want to write it concisely, you will say Gaussian with covariance matrix identity. That means everybody has variance 1 and everybody is independent from rest because you see zeros all over the place. Okay. And now where do this type of vectors show up? Where do they concentrate? And turns out they concentrate around norm root n. Let me try to illustrate it. So what we are saying is, like, with high probability, the norm of your random vector comes out something like this. If I would try to do a bad picture, it's like you take the square root of n radius sphere. As we computed, this is about the volume 1 threshold almost. And then your random vectors, turns out they come up around 1 plus and 1. This was even worse in my standards. Okay. Like this. It comes out in this shell. This is 1 square root of n, 1 minus epsilon, square root of n, 1 plus epsilon. If it would be literally square root of n, it's going to be on that sphere with radius square root of n. It's coming around it, but not exactly on it. And if I would be drawing better, this shell would be looking thin. They call it thin shell concentration. Okay. So it's just, your vector is going to have a norm about square root of n, basically. It's around that area. Turns out that's how it concentrates. Okay. Now, I want to tell you why, but before I want to tell you how are we going to use this at all. Okay. So before I tell you why this is the case, the way we will use it, the tool that you build up off of this is called Johnson-Lindenstrauss flattening lemma. So I'll walk you through this. There's a technical statement right here. But before I walk you through this, what does this mean and when you would use it? So you have a lot of data in high dimensions. Your purpose is to reduce the dimension of the data. Okay. First thing you need to ask yourself is, what do you want to preserve? If you would like to preserve the entire structure of data, probably you will do PCA or a version of it. But this is not always what you care about. Sometimes you only care about if these two vectors were close to each other or not. You care about similarity. Then the only thing you care about is distance between the vectors in your data set. Okay? If that's the case, this is the standard tool. There is some improvements of it, but still it is hard to beat. Okay? So you want to reduce the dimension of your data. The only thing you care is the distances between your data points. Okay? In that case, this is what you would use. And this shows up in so many places, geology, biology, computer science, whatever. So this paper gets, cited by anyone. So I was lucky enough to take a course from Johnson in grad school. This guy spent 60 years of his life working on something called Banach space theory, very pure math. And he was saying that he hates this little lemma. And I dared to ask, why do you hate it? He's like at that point, maybe 70-something-year-old professor, almost 80. He was still very sharp, though. Said, I worked on this theory 55 or 60 years. I solved very hard problems after many years of working. Some of them took me 5 years to solve. And then this thing, we were trying to solve a hard problem, we couldn't. Then he asked to his collaborator, Lindenstrauss from Israel. So Yoram, his name. Yoram, what would be an easier version? They write it on the board, they cannot solve it anyway. They make it easier. Eventually, they write this thing on the board. They solve it in 15 minutes, and they write the paper in like few hours. And that's the citation that paper gets. Everything else he did in his life, sum them up, multiply by 5. This is more. so then he says, that's why I hate it. I worked so hard, nobody cares. Anyway, so now what is this tool? This is your data points. You got n of them, and you imagine this D is very big. too many features in your data, okay? You would like to reduce the dimension. What do? You create a random matrix, okay? And that random matrix will be this many rows, logarithm of n divided by epsilon squared. Epsilon is your tolerance for error. Yes. And this many columns. Now, before we do anything, I created a matrix. Suppose this is K by D. And I'm going to take that A, multiply with one of my data, say A times X1. And X1 was living in RD already, right? But observe that A times X1 will be in RK if my matrix was K times D. So effectively, my data went from D features to K features. That's the dimensionality reduction, okay? So after you multiply all your data points with this matrix, everybody is going to go from this dimension to this dimension. And it's just logarithmic in terms of the number of data points you see. And as you see, this does not care at all about the previous dimension. It only cares about how many data points you got. And the dependence is logarithmic, okay? So when you first see it, it looks like maybe magic. And the way to prove it is exactly the Gaussian concentration I showed you. The proof is not magic, okay? I have many stories about this lemma I can tell later. I just remembered a guy from IBM thinking this is just something we made up on a board in a conference. So we were discussing something. Apparently there was a guy from IBM on he was working on their linear programming software, research scientist. Leo, somebody, I forgot the last name. And this guy shows up and says, what you wrote here is just a wish, right? We're like, no, that's a theorem. It's like, this can't be true. It's too good. No, it is a theorem. It took the guy a couple of hours to internalize this is actually the truth. Okay, so it's so good. That's the point. Okay, so what do? You multiply all your data points with this matrix, and you say you got xi data point and xj data point. They had a distance, and after you multiply with the matrix, you take the distance between a times xi minus a times xj. And it is the same thing as a xi xj. This is what's written here. And this, take it as your matrix. So you create a random matrix, you need to scale it, right? The distance, the loss you have, correct distance versus what you got after projection is at most epsilon times the distance itself. So this gives you an epsilon approximation to every single pairwise distance in your data set, just by one shot. Okay. So you create this matrix, Gaussian, it doesn't have to be Gaussian. Later, people figured out even +1 with coin toss works. Okay, so it's got to be, say, take it easy, Gaussian with unit variance, every single entry of that matrix. The size of it should be this times D. And to get things right, you need to divide your matrix with 1 over this number just to scale correctly. And that's it. You apply that on all your data. With very high probability, you will be preserving all your pairwise distances. And the way to prove it is by the Gaussian concentration. I'll tell you a little bit about it. I have time. But now, before maybe telling you about this Gaussian concentration and how this came to be, we can maybe think about what kind of applications this could be useful for. Like any problem that comes to your mind that you could use this right away. Well, for example, if you're working on clustering, it's all about pairwise distances. You can just use this right away. Instead of clustering right away, first use Janssen-Mills, then cluster. The clusters you get wouldn't be so different, but you could get it much quicker if your data was huge. Or what else? Like, say it again. Recommendation. So you mean like similarity, maybe? Yeah. If you're looking at, again, yeah, the user, trying to locate the user close to another thing in your database. The only thing you care about, how distant they are, and this is what is preserved. I don't know, maybe you could even try it on, if you're training a density-based estimator, let's say K nearest neighbors. density estimator. If this didn't make much sense, don't worry, I'll talk about it next week. But it's a standard technique, right? KNN. Again, nearest neighbor probably not going to change so much with this, etc. So anytime the only thing you care about is pairwise distances, you could plug this. Yes, go ahead. Very good question. So you put the words on a very high dimension. Yeah, after the embedding, yes. Yes, that's right. Of course, there the main hard problem though is find a good embedding. Suppose somebody has done it already, then you can do this. That is true. In the inference part, right? Yeah, that is true. Very good. Thank you, Ben. All right. So let me try to walk you through how you build up this tool. So I need to first tell you this Gaussian concentration. Then we will use Gaussian concentration to prove something about random matrices, and that's going to be about it. And I'm not going to be able to do it all, but let me show you the Gaussian concentration at least. The fact that Gaussian vectors comes on in this thin shell. Okay, so what we would like to prove is this. Norm of your vector being around square root of n with the error epsilon times square root of n. This is smaller than square. So norm is a weird thing. I have squares and square root. I don't want to deal with it. If I would have the norm square, that's going to be nicer. X1 squared, X2 squared. So I want to relate it with something with the square root of that norm. So you play with a little bit and you end up saying, you know, if this is about root n, I want this guy to be about n. And this probability is always bigger than this one. So you can just go with bounding this one. So square of your norm, I'm trying to prove it's almost always about n. There's a strong concentration. How am I going to go about it? Well, let's go step by step. So first of all, what is this thing? It is squares of all your coordinates, right? And all those coordinates are Gaussians with unit variance. Okay. And I would like to understand the behavior of this random variable. Okay. First of all, what is the expectation of this guy? Well, the expectation of this is 1 because variance is 1. And then 1, 1, 1, 1, 1, you get n. So then things start looking nice. What you're asking here is actually your random variable minus its expectation not being so much bigger than epsilon squared times the expectation. So then this starts looking like a reasonable thing to ask, okay? And how would I do something like this? I would use an idea that I talked about in last lecture called Chernov's idea. It goes through moment generating functions. It's a very important idea, so that's why I want to go through it again in this context, okay? How does that work? You first reason about the moment generating function of your random variable. So what was the moment generating function? Here is the definition. You take your random variable, multiply it with a number t, take it to the exponent, take expectation over your randomness. That's called moment generating function at point t, okay? That's the definition of it. And the reason this is called moment generating function is this function records all the moments of your random variables. If you know this guy, whatever that function is, you know the expectation, variance, third moment, fourth moment, you could generate whatever, okay? This we talked about last lecture. If you want, you can take a look. And then this guy is a summation of independent random variables. So in that case, moment generating function ends up being multiplication of those moment generating functions. The summation here becomes a multiplication in this world. So since they all are the same thing, I'll end up multiplying moment generating here, times that, same thing n times, so that same thing gets to the power n, okay? So, all right, then all you need is to compute this moment generating function, whatever that is. It's just square of a Gaussian. And you do that, it comes out as the bound you get for your moment generating function is your moment generating function, turns out, is always less than e to the n times t. And now you could forget everything you heard so far. Now let me show you the idea. So I would like to see the probability of my random variable being bigger than n plus this, okay? I could raise everybody to power e to the t. This is gonna be the same thing. I'm multiplying left and right with a number, say 5, then I'm putting them on the exponent. Nothing has changed, okay? So I'm looking at this probability. Then how do you bound this probability? This is always less than expectation of the stuff here divided by whatever there. This was called Markov's inequality. If you remember, let me write it for you. So what I'm saying is, like, if you have a non-negative random variable x being bigger than some threshold alpha was less than expectation of that random variable divided by alpha. This is something we talked about earlier. And that's exactly what you're doing. Expectation of this is the moment generating function. The thing on the right-hand side is whatever the thing on the right-hand side is. And then for this, we got a bound. You plug it in. It was n to the t. And then there's minus this here. And you realize n to the t minus n2 will cancel. You'll end up with this. And this is more or less literally what I was claiming in Gaussian concentration. The t, you could pick whatever t now. This works for any t, okay? So let me circle back to my claim. My claim in Gaussian concentration was this being around root n is bounded by 3 times what I was just writing there. And there I cheated. I only did one part, not the absolute value, but it's symmetric. So I end up doing the same proof twice, and that's what the bound you get. Okay. So the proof is basically go through moment generating function, do your computations, you end up getting the result. Okay, now that I have the Gaussian concentration, how do I build up that Johnson-Distrust thing? Well, now let's go slow. I had n data points, right? And I wanted to talk about all pairwise distances. So you could pick any pair xi and xj. And you could look at that distance. How many such pairs you could pick? Let me see if you remember your combinatorics. And choose 2, right? So you're picking 2 from n. This is what this thing stands for, right? And it's roughly speaking, I times j is not a bad approximation. It will be n times n squared. This guy is like n squared over 2. You know, you weren't so bad. You just counted everything twice. ij and ji is the same thing. So more or less. Okay. Now, I would like my matrix A to get on this stuff. And I want to have some estimate about this minus the actual distance. That's what I care about, right? This is what I care about. So I have actually and choose too many estimates to make together. Okay. So what we will do is, like, we will get a bound for one of them. Say for one of them, the probability that things can go bad is at most, say, 1 out of a million. Then what is the total probability of going bad? 1 out of a million plus 1 out of a million plus 1 out of a million this many times. You sum up all the bad probabilities in all the pairs. If you get your bound very good for one of them, you have the budget to pay off for summing up this many times. Normally, it looks like this is a huge number, you know, and it's big already. So how am I going to pay off for this? Turns out your bound is in the form of like e to the minus n. So it can pay off for n squared very easily. Okay. So the bound you end up getting comes out in this form. And how would you prove it is, again, not magic. So you got your matrix A. And suppose you have whatever vector here, V, right? And this matrix is Gaussian. Take the first row, multiply it with V. Let me write it down. A11, V1. A12, V2. A1D, VD, right? So this will be multiplication of first row with your vector. And your vector is deterministic. This A stuff is random. And what is that A stuff? They're Gaussian. If you remember, sum of Gaussians is again a Gaussian. So at the end, this comes out just one Gaussian for one coordinate. And you're going to have whatever dimension you put here, k say. You will have k such sums. And all those sums will control coordinates, and you'd like to understand what happens with that coordinates. Basically, you just plug in the stuff you already created for that new vector, and this gives you the result. Okay, again, there is some technicality for this, but I don't want to do that now. So more or less, you plug in the Gaussian concentration for the vector you created. That gives you this theorem. And then off of this, you repeat it and choose too many times. You end up getting Johnson-Lindstrauss. And the only reason we are able to go to this dimension is you raise it to the E minus. That kills off that n squared. And that's the limit of this idea. Later, people worked on improving this. I think there's nothing you can do with ln, but maybe you can improve the dependency on epsilon. There is, I think, just an epsilon version. They also thought about, can I cheat, not compute the whole Gaussian matrix, even randomized thing. And they created something called fast Johnson-Lindstrauss. People keep working on that. So I don't know what portion of that fancy ideas got implemented and used, but this is very useful and being used. This is, you can, code up yourself in a sector. You're literally sampling Gaussians, putting them into a matrix, multiplying with your data. So there is a whole bunch of work on this. If you want to check the latest status, you should Google fast Johnson-Lindstrauss or optimal results for Johnson-Lindstrauss. There's a very cool person working on it. If you're interested, I would say go to his website. His name is Jelani Nelson. I think he currently moved to UC Berkeley. And he's originally from the Virgin Islands. Half from Virgin Islands, half from Ethiopia. Pretty cool guy. All right, that's all for today. Thank you so much.